Hi, this is Babak. In this video I'm going to solve the following problem for you. Let me read the problem for you first. 10 players play in a tournament. Each pair plays one match, which results in a win or a loss. If the kth player wins x sub k matches and loses y sub k matches, show that x1 squared plus x2 squared up to x10 squared equals to y1 squared plus y2 squared up to plus y10 squared. This problem has been chosen from the Mathematics Olympiad of Soviet Union 1987. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. Okay, so if you want to solve this problem, there are some things that I want to mention. So here, assume that, first of all, I want to know how many matches in total are there. So we know that each player plays with everyone else. So it means that player number 1 plays 9 games, player number 2 also plays 9 games, and etc. etc. until player number 10 also plays 10 games. So if I ask you what is the total number of games, the total this would be equal, we have 10 person, each person plays with 9 more. But of course, if I write 90, I am counting each game twice, yes, because when player 1 plays against player 2, simultaneously player 2 is also doing the same game against player 1. So the total number of games is not actually 10 times 9, but it is half of this number, so that would be 45 games. Okay. On the other hand, if I ask you what is x1 plus y1, then you can immediately answer this. x1 is the number of wins for player 1, and y1 is the number of losses for player 1. And we know that if I add them together, it would be the total number of games that person 1 has played in this tournament, which is 9, yes? But this can also be said about x2 plus y2, yes? Regardless of how these games are being played, we know that x1 plus y1 should be 9, and x2 plus y2 should also be 9, because we either in each game one player either loses or wins. There is no draw there, okay? Okay, and then this will continue until the last person, x10 plus y sub 10 is also equals to 9. Yes, this is for sure. Another thing that I want you to know is that what happens if I start adding x1, x2 up to x10, This becomes exactly the total number of games, yes? So this becomes 45, because each game corresponds to one loss. So one win here, yes? So it means that the number of wins by player 1, the number of wins by player 2, if I add them, all of them, this becomes the total number of games. And of course, this is also true if I write y1 plus y2 plus up to y10. This is also equals to 45. This is the total number of games again. Okay. But now I want to prove this equality, and in this equality I see that I have powers of 2 involved. One possibility is probably thinking raising these to power 2 and start adding them up. Of course, that's not a good idea, because if I square this, then I will get x1 squared, which is good, y1 squared, which is also probably good, but then 2 times the first one times the second one will be left for me, and then I don't see any track of these kinds of terms in the equation that I want to prove, in the equality that I want to prove. So that is not a good idea. What can I do then? So from here I can conclude that x1 is 9 minus y1. And from here I can conclude that x2 is 9 minus y2. And finally, from here I can conclude that x sub 10 is equal to 9y sub 10. Yes? And now here on the left hand side of this equality, what I have is x1 squared plus x2 squared up to x10 squared. Yes? And instead of x1, I can put 9 minus y1 here. Instead of x2, I can put this one, and until instead of x sub 10, I can put this. Okay, so what happens? It becomes 9y1 squared plus 9 minus y2 squared and plus up to 9 minus y10 squared. And now what can I do? I can expand each one of them, so this becomes 81, 2 times the first one times the second one, so it becomes 18 y1 and plus y1 squared. This is the expansion of the first expression, and the second expression is more or less similar. So it becomes the first one squared, 2 times the first one times the second one, and finally the second one squared. And then this will continue until the very last term, which is also similar. The first one squared, 2 times the first one times the second one, and then finally I have, the second one, and then finally the second one squared. But then you see, I have 181 here, 81 here, 81 here. How many 81 ones appear here? 10 times, yes? So it becomes 810. And then between this term and that term until this term, I can factor a minus 18 out. So what is left is minus 18. And then I have y1 plus y2 up to y sub 10. And then I will have y1 squared plus y2 squared up to y sub 10 squared, yes? But here we learn that this sum is exactly equal to the total number of games. So what happens, I would write 810 minus 18 multiplied by 45 plus y1 squared plus y2 squared plus up to y10 squared. But if you calculate this number is equal to 0, because 18 times 45 becomes exactly equal to 810, and then this becomes 0, and what I get is just y1 squared plus y2 squared plus up to y sub 10 squared, and that is exactly equal to the right hand side. So, and that was the proof of this equality. One common mistake that I have learned from some of my students is that they are thinking that we can solve this problem easier, saying that actually x1 up to x10 and y1 up to y10 are essentially the same numbers appearing in different orders. So if that is the case, then of course it doesn't matter how we add them up, the left hand side becomes equal to the right hand side. Of course, it might be that this is the case for some possible scenarios, but this is not guaranteed that the numbers that appear on the left from x1 up to x10 are exactly the same numbers that appear on the right from y1 up to y10, just in different orders. It might be that this is indeed the case, but you can cook up scenarios that this is not indeed the case. And I want to convince you that this is not the case. Let me make it a little bit simple. Instead of 10 people getting involved, let us just consider 4 people, yes? So what we do, so let me just draw 1. So how can I imagine that? That's also good to know. How can I want to convince you that this is not the case. For example, consider this scenario that we have only 4 players, and they are playing against each other, and then assume that the person number 1 wins all the games. So it plays against the rest 3 people, and then it will win all the games. So x1 would be 3 in this case, and then y1 becomes 0. Yes, because there are 4 players. I am assuming that for this example there are 4 players. The player number 1 wins all the games, so it loses nothing. Yes, and now assume that player number 2 wins 1 game, player number 3 also wins 1 game, and player number 4 also wins 1 game. So then it means that y2 is 2, y3 is 2, and y4 is 2. So this is actually quite possible. You can immediately convince yourself that this is a possible scenario if there are only 4 people participating in the tournament. And then if you see, these numbers are not these numbers. Yes, but still you see, if I add these pairs, they are 3. If I add all of them, it becomes 6, which is of course the total number of games. Why? Because here in this case we have 4 times 3 divided by 2, which is 6. So in total we have 6 games. And if I add these 4 numbers, it also becomes 6. But you see that these numbers in the first list are not the same numbers in the second list. But if I square them and add them, this becomes 9 plus 1 plus 1 plus 1, which is 12. And if I square these numbers and add them, it becomes 0 plus 4 plus 4 plus 4. It's still 12. Yes? So you see that I can cook up some scenarios in which the numbers appears as x's are quite different from the numbers that appears as y's. So I cannot say that these are the same numbers. But still, the sum of the squares of x's is equal to the sum of squares of y's. So for example, let me also tell you something. How did I come with this example so easily? For example, what I'm saying is that I imagine that I have 4 players and I put 4 dots here. So let me call this one player number 1, this one player number 2, this one player number 3, and this one player number 4. Then I imagined a scenario that 1 wins everyone. So what I did, I draw a line from 1 to 2 and I put an arrow here. So if I put the arrow in this way, this means 1. For example, I interpret this, it means 1 wins 2 in the game between 1 and 2. If 2 wins 1, I will draw this line segment, but I put the arrow in the other direction. Okay, so here I imagine this case that 1 wins everyone. So I draw an arrow from 1 to 3, from 1 to 2, from 1 to 3, and from 1 to 4. Yes? Then I imagine this triangle that 2 wins this game, 3 wins this game, and then 4 wins this game. Yes? So you see that this was the geometrical picture behind my mind to be able to cook up this example immediately. Okay, so this is possible. You see, 1 wins everyone, but no one is lost, is being defeated by everyone. So this means that I will have a 3 in my X list without having a 3 in my Y list. So that was my intention when I was trying to make up this example. I was thinking that let me consider a scenario in which one person, here number 1, wins all the games. So it means that I will have a 3 in my X list. I wanted to convince myself that this is possible, that 3 does not appear in the Y list. It means that I need to cook up a scenario in which there is no one which is being defeated by everyone. And then I come up with this diagram and I realize that I can make that happen. Okay, so these kind of things is a branch of mathematics which is called graph theory, and hopefully if you continue your lessons we will actually cover those topics which are important with in mathematics Olympiads or in mathematical contests. Okay? Okay, so I hope that this video has been useful for you. Until the next video, be safe and goodbye. Thank you.